So now we're going to pull together all of our skills to solve general systems of linear equivalences in one variable. Some of the bases might be coprime, some of them might not. Let's just see what happens. Here is our first example. Find the smallest positive solution or show that there is no solution to find. We have three equivalences. We want to find an x that is equivalent to 2 mod 5, 1 mod 8, and 5 mod 12. Now our three bases are not relatively prime to one another, but 5 is relatively prime to 8 and is relatively prime to 12. Therefore, whether a solution exists or doesn't entirely depends on whether I can find something that solves these two simultaneously. If a solution here exists, there is one solution modulo the LCM of 8 and 12. And the LCM of 8 and 12 will definitely be relatively prime to 5, so I'll then have two equivalences with relatively prime bases, and then I know solutions exist. So whether or not solutions exist entirely boils down to whether there is a solution to the two equivalences whose bases are not relatively prime. However, let's just check. Do there exist solutions to both of these simultaneously? So I need to compute the greatest common factor of 8 and 12, that's 4, and then ask, is 1 equivalent to 5 modulo that number, 4? Yes, 1 is equivalent to 5 mod 4. So there are solutions to this pair. There will be a unique solution modulo the least common multiple of 8 and 12. Since that's definitely relatively prime to 5, I can then just claim there is a solution overall, and then I can try to find it. Now, just using the brute force technique on the previous slide, I just list out 1, and then I start adding 8, and I keep checking mod 12 until I find a solution. 1 is not equivalent to 5. Add 8. 9 is not equivalent to 5. Add 8. 17 is equivalent to 5 mod 12. So these two equivalences here can exactly be replaced with just a single equivalence, x equivalent to 17 modulo the least common multiple of 8 and 12, which is 24. So I still have this equivalence here to worry about, but I've replaced these two with a single equivalent statement. And now I have relatively prime bases. And we in fact see pretty quickly 17 is clearly the smallest solution to the second one, but that's already a solution to the first one. If nothing else, you can just apply the Chinese remainder theorem and use the algorithms developed in earlier lectures. So x equals 17 is one such solution. However, that actually tells me that all solutions must be equivalent to 17 mod 120. And 17 is the smallest positive integer that is equivalent to 17 modulo 120. So we found the smallest positive solution, and we had to combine techniques from various places. Let's do another example. Again, find the smallest positive solution or show that there isn't one to find. We have three equivalences, 2 mod 10, 4 mod 6, 7 mod 15. No pair of bases are relatively prime to one another, so let's just do this by attacking one pair of equivalences and seeing what happens. 2 mod 10 and 4 mod 6. So what we have to do is check, are there even solutions to find? Yes, the GCD of 10 and 6 is 2, and 2 and 4 are equivalent modulo 2. So now can we find a solution to both of these now that we know there is one? So we start with 2 and we keep adding 10 to it, and I simply check modulo 6. Is 2 equivalent to 4 mod 6? No. Is 12 equivalent to 4 mod 6? No. Is 22 equivalent to 4 mod 6? It sure is. So 22 is a solution to both of these. So now instead of having these two equivalences, we have solved that both of these are solved exactly when x is equivalent to 22 modulo the least common multiple of 10 and 6, and that least common multiple is 30. So these two here, I replace with one equivalence like this, and now I start adding the next one in and ask, well, now I've got two equivalences. 22 is equivalent to 7 modulo the GCD of 30 and 15. So there are solutions, and there is one solution modulo the LCM of 30 and 15, which is 30 again. So there's only one solution mod 30, but it has to be 22 mod 30. So there's only one solution modulo 30, and it has to be 22 mod 30, so hopefully 22 mod 30 is the only solution. And indeed, 22 does solve this equivalence as well. So x equivalent to 22 mod 30 actually describes all solutions and is already the smallest positive solution, 22. A third and final example for this quick little video. Find the smallest positive solution or show that none exists. We've got 4 equivalences here. 2 mod 12, 4 mod 14, 8 mod 18, and 10 mod 20. Let's go pair by pair. Let's just look at the first pair. The GCD of 12 and 14 is 2. 2 and 4 are equivalent mod 2. So there is a solution, and there is one modulo the LCM of 12 and 14, which is 84. So starting with 2 and adding 12 and checking what's the value mod 14, 2 is not equivalent to 4 mod 14, add 12. 14 is not equivalent to 4 mod 14, add 12. 28 is not equivalent to 4 mod 14. Keep going, okay, listing out all of these things. The first solution to x being equivalent to 4 mod 14 is 74. So this pair of equivalences gets replaced with equivalent to 74 modulo that LCM, 84. And then I still have these 2 equivalences hanging around. Okay. Let's take a look at these 2 equivalences. The greatest common divisor of 84 and 18, well, remember 84 was 4 times 3 times 7. 18 is 2 times 9. So the GCD is 6. 74 is equivalent to 8 modulo 6. So there will be a solution, and there will be a unique one modulo this LCM, which turns out to be 252. So we start with 74, we add 84 successively, and keep checking modulo 18. The first one to x being equivalent to 8 modulo 18 is this last one, 242. So these 2 equivalences can now be replaced with x is equivalent to 242 mod 252, and I still have this last one hanging around, x equivalent to 10 mod 20. 242 is in fact equivalent to 10 modulo this GCD, so there is a single solution modulo this LCM. So we do the same technique. We list out 242, then we add 252, add 252, add 252, and we keep checking what are these modulo 20. The first time we're actually equivalent to 10 mod 20 is here. So solutions are given by x is equivalent to 1130 mod the LCM, which we computed to be 1250. And the smallest positive integer that satisfies that is 1130. So 1130 is the smallest positive solution to this following quadruple of very much not coprime base linear equivalences. So 3 examples to kind of ramp up the difficulty. The easiest thing that can happen, by the way, is at some point we might have found that 2 target values were not equivalent modulo the greatest common factor of the 2 bases, and at that point you would simply say there is no solution at all. I just wanted to go through a couple of ones that did have solutions to show the steps.